Tentuka. Kami ucapkan selamat datang peserta webinar Geoinformatika. Melati kuntum, tumbuh melata, sayang merebah di pohon cemara. Assalamualaikum mulanya kata sebagai salam pembuka acara. Baik, yang terhormat Head of the Geoinformatics Research Center, Electronics and Informatics Research Organisasi Nasional Riset and Innovation Agency, Profesor Dr. M. Rokis Komarudin, MSc. Selamat pagi, Bapak.
Selamat pagi, Pak Dedi.
Okay. Respected to great speaker today, Mr. Min Sik Kim from Nara Space Technology. Morning, Mr. Kim.
Hello, good morning.
Morning, okay. And then Mr. Professor Danang Surya Chandra-Esi, MSc, Researcher Professor Geoinformatics Research Center BRIN. Morning, Mr.
Good morning, Pak Dedi.
Morning. Specific to moderator today, Mr. Yohanes Fridolin dari SCM.com, Geoinformatics Research Center BRIN. Selamat pagi, Pak Yohanes.
Selamat pagi, Pak.
Pagi, oke. Okay, ladies and gentlemen, great student of the Geoinformatics Research Center, colleagues of committee, BRIN academics, universities, BRIN partners, and all bright series participants who attended and listened to this event from Zoom meeting and YouTube live streaming. Good morning. Okay, we would like to welcome to participant practitioner of bright talks about Informatika Hot TopicS. Today, Tuesday, just 28 and 2025. BRIN is a series of webinar activities held by the Geoinformatics Research Center, Electronics and Informatics Research Organization to discuss various topics related to geoinformatics, the technology in Indonesia. Okay, before continuing the event, let me introduce, I'm Dedi Ahmadi in Public Relations to get to this event. Okay, backstage, before our event begin, allow me to read out today's event guide. Number one, participants should mute their speaker with speaking and use the raise hand or chat box to ask question. Number two, participant welcome to change the name to, for example, Karim _BRIN. And number three, participant are welcome to change their Zoom virtual background to one of the provided ones. Number four, participant can join this webinar from BRIN Indonesia YouTube channel if Zoom capacity is insufficient. Okay, ladies and gentlemen, let us now listen to the national anthem, Indonesia Raya. We ask that you listen with reference. Ladies and gentlemen, we will continue. Welcome from the head of the Geoinformatics Research Center at BRIN to Profesor Dr. M. Rokis Komarudin, SI, MSc. Pada Bapak Rokis, saya persilakan.
Baik, terima kasih Pak Dedi. Thank you very much. Ladies and gentlemen, speakers, distinguished guests, and also citizens. Assalamualaikum warahmatullahi wabarakatuh. Good morning. Alhamdulillah, it is a great pleasure and gratitude that we gather here today for successful implementation of BRIN, a BRIN talk about Geoinformatics Hot TopicS, series number 8, with title Enhancing Satellite Imagery, the Power of Super Resolution in Remote Sensing. I would like to extend my deepest appreciation to the distinguished speakers, especially from Naraspace, Mr. Min Sik Kim, South Korea, and of course, Professor Danang Surya Chandra from our research center from BRIN. Your valuable time and insights are truly appreciated. Today, we are here to discuss a topic that is crucial in advancing remote sensing technology, that is super resolution. As we all know that the sharpness and clarity of satellite imagery play a vital role in improving the quality of data use for various purposes, for environmental monitoring to urban planning. The ability to enhance low-resolution image and make them sharper, it is a game changer for industries and research areas. At the Geoinformatics Research Center, particularly in the Geodata Research Group, which is Professor Danang as head of research group there, this is at the core of our focus, and we are constantly striving to develop and refine technology that enable us to extract more valuable insights from satellite imagery. Super resolution is a key improving the quality of remote sensing images, and we are committed to advancing this technology to better serve our scientific and social needs. The exciting part is the role of artificial intelligence in this development. We firmly believe that integration to AI into super resolution technology will significantly enhance. AI has the potential to speed up the process, increase accuracy, and also unlock new possibility for geospatial research. It is our hope that as this technology evolves, it will provide solutions that address the growing demand of environmental monitoring, disaster management, and also for the other crucial areas. Finally, I would like to take a moment to express my sincere thanks to the organizing committee for making BRIN number 8 possible. It is through their hard work, dedication, and also teamwork that we have this opportunity to learn and exchange ideas and continue moving forward together. Your efforts are greatly appreciated. Once again, thank you to all our speakers, participants, and attendees, and also participants for your presence and engagement today. I look forward to the profile discussion and collaboration that will continue beyond in this event. Thank you very much, and continue work together toward advancing for the better future, and very nice discussion, and also successfully conducted this webinar. Thank you very much, and back to Mr. Dedi. Thank you.
Okay, thank you for your welcome and information, Prof. Rokis. Okay. Okay, break citizens. To document today's activities, we would like to ask the participant and attendees to open their video camera for a group photo. Mohon bisa dibantu.
Baik, Bapak. Bapak Ibu sekalian, mohon izin untuk
membuka kamera saat tindakan sesi dokumentasi. Akan saya hitung 1, 2, 3. Baik, sekali lagi. 1, 2, 3. Oke, terakhir sekali lagi. 1, 2, 3. Baik. Sudah, Pak. Saya kembalikan lagi kepada Bapak MC. Terima kasih.
Okay, thank you, Xavier. Okay, entering the main event, we have a presentation and discussion. I invite Bright's moderator to join us today. Good morning, Mr. Johannes Brendolin. Selamat pagi, Pak.
Good morning, Mr. Dedi. Selamat pagi, Pak.
Sehat ya, Pak ya? Oke, baik.
Sehat, Pak.
Oke, thank you. Pertama, I will read this curriculum vitae Mr. Johannes. Name is Johannes Fridolin Estrio, SSC MCOM, from Geoinformatics Research Center BRIN. Education background, Bachelor and Master in Computer Science. Job experience, Technical Policy Review in Geoinformatics Research Center BRIN. Active researcher in the field of geoinformatics and remote sensing. And international publication in Scopus and IEEE. First author in journal IEEE Access Q1 about remote sensing and image fusion. And then cloud detection research, NOSQL for remote sensing data, agriculture monitoring, oil and gas exploration. High index Scopus 3, more than 20 publication. To Mr. Johannes, please to get even today's. Persilakan, Pak Johannes.
Terima kasih, Pak. Okay, thank you, Mr. Dedi, as the MC this morning. Good morning, everyone. It's my pleasure today to moderate today's Bright Series 8 session. My name is Johannes Fridolin, and I have the honor of the moderating today's sessions on the enhancing satellite imagery, the power of the super resolution in remote sensing. Today's topic addresses one of the most pressing challenges in remote sensing, the spatial resolution limitation that constrain detailed analysis of satellite imagery. Super resolution techniques represent a paradigm shift in how we can extract maximum value from existing satellite data sources, particularly relevant for Indonesian diverse geospatial application. Now, let me introduce our first speaker, Mr. Min Sik Kim, joined us from NARA Space Technology, where he served as Vice President Business Development and co-founder since 2015. Mr. Kim holds a master's degree in astronomy and bachelor degree in mathematics and economics from Yonsei University. He has been instrumental in developing an Earth paper platform which integrates super resolution and AI data analytics for satellite imagery enhancement. His expertise spans remote sensing and deep learning application, including his work developing disaster analysis algorithm for Korea Aerospace Research Institute. His unique combination of academic background in astronomy and mathematics, coupled with extensive industry experience, provides valuable insights into the practical implementation of super resolution technologies. Okay, good morning, Mr. Kim.
Good morning, Johannes.
Okay, Mr. Kim, the floor is yours for the next 45 minutes. Please proceed with your presentation. Thank you.
Thank you. Can you see the screen?
Yes, I can see.
Okay, so hello everyone. I'm Min Sik Kim from NARA Space. It's a great honor for me to participate in this webinar. I'm here to present the super resolution technology overall, some trends and what kind of activity we're doing in the scope of super resolution, and some additional ideas how we can implement in the Indonesian domain. So first of all, I will just for some of you who may not know about our company, I'm going to introduce very briefly about our company first. We are a 10-year company now. We are based in South Korea, Seoul, and Busan. And we are now with 75 people of excellent engineers, and we have accumulated 24 million USD until now of the Series B phase, and we are planning an IPO at the end of this year. This is some of our company overview, and when we introduce our company to others, we say that we are providing end-to-end service from designing and manufacturing the CubeSats, and also we do mission operations and data acquisition after we launch the satellites. And after we get the data from the satellite, we provide value-added service and insight contents to our customers. And here is some of the overview of our satellite data solutions. Currently, we are preparing two satellite constellation that can contribute in two ways. So first series would be Observer. It's a 1.5 meter GSD multispectral satellite. The first one was launched in 2023 and still operating quite well. And then the next launch is planned for November this year. And beside Observer, we are also preparing a very unique satellite called adalah. It's dedicated for methane detection, and the launch will be next year. And these are some of the images that we have acquired using Observer. And on the right side, you can see that the smoke from the wildfire and the location is the Palisades that has happened at the early of this year. And this is some of the zoom-in shot of the Observer satellite. The resolution is mid-resolution, but it's powerful enough to detect planes that is located in the airports. And this is some more detailed information about adalah. It's a hyperspectral imager, and it has actually two cameras dedicated, one for visible near infrared and one for sphere bands. And the sphere band camera is actually hyperspectral with very narrow spectral resolution. And our main objective for the adalah is to pinpoint high emission methane sources that is over 100 kg. And our plan is to launch a 12 satellites constellation with the 4 number planes to cover global scale and provide low latency data. And as a future plan, we are planning to launch 74 satellites combining Observer and adalah all together within 5 years. And from now on, I will go briefly about our satellite data analytics solutions. So we are currently focusing on 5 key sectors: finance, agriculture, natural disaster, environment, and defense. And currently, we are providing our solution on a platform called Earth Paper. It's a live platform that provides not only the satellite data, but also insight contents that you can just click and read, so that you don't have to do any image analysis on your side. You can just read the blog post and then make decision. And from now on, I will go over the super resolution technology overall. First, I will begin with how the technology has evolved from the past and how it has reached until now. And then I will go on by explaining what is different, what different technology Naraspace is using in regarding super resolution. And I will add some more use cases as well. So super resolution is it's very simple to explain. So it's a technology that can enhance the spatial or maybe the resolution of the images from low resolution to high resolution, and the methods are very various. So overall, there were some classical methods before the advent of the AI, and before the sorry. Sorry, yeah. Before deep learning, superposition was mainly approached with classical methods, and there were two main categories. And one was the interpolation-based method. So the algorithm decides how to guess the values of new pixels based on their neighbors. So for example, nearest neighborhood just copies the closest pixel, and bilinear and bicubic use weighted averages. And in case of the model-based methods, was to treat the low resolution image as a degraded version of the high resolution, and then try to solve it some kind of inverse problem in mathematically speaking. So dictionary learning was a popular approach. So we learn from the pairs of dictionaries of the low resolution and high resolution image patches. And then when we give a new low resolution patch, we find its representation in the low resolution dictionary and use it to reconstruct the corresponding high resolution patches. This method can sharpen the edges better than interpolation, but it's computationally expensive and struggles with complex structures. Sorry, yeah. So while classical super resolution methods were important first step, they have some critical limitations that prevent from recovering the true details. So first one would be there is no new information when using the interpolation-based methods. So interpolation methods like nearest neighborhood or bilinear, they just use the pixel values by using the averaging neighbors. So this means that no new details can be added. Something like small objects like cars and building edges and vegetation patterns, they are not possible to appear. So as a result, the images itself gets larger by using the interpolation, but they're still blurry and over-smoothed, as you can see on the right side of the image. And in case of the model-based methods, reconstruction or dictionary learning methods try to solve this by using handcrafted priors, such as edge sharpness or smoothness. But such methods sometimes produce plainer edges than interpolation, but the textures often look very artificial and repetitive, and that means not natural. And because they rely on the handcrafted math assumptions, they couldn't model the complexity of the real-world data, such as irregular vegetation or complex urban structures. So that was the kind of limitation of the classical methods. And then what happens is deep learning comes in. So deep learning fundamentally changed the super resolution, and the center of this breakthrough was the convolutional neural network, or CNN. And please remember these slides very well. So this is how overall deep learning-based methods train their super resolution network. So they normally train with a paired data set. So when they have this one high resolution data set, they generate some low resolution that matches with the high resolution, and then they train with this. And then after they finish the training, they use this super resolution network and apply it on the high resolution, so that you can upscale the original GSD. And as I mentioned, the convolutional neural network was a center of this breakthrough of the technology. Just to give you a brief background of what CNN is. CNN is a deep learning-based model designed to process data with grid structure. So it's kind of images that is made of 2D pixel grids. So instead of training each pixels independently, CNN uses convolution filter that is also called corners, and that slide across the images. So these filters are trained automatically detect meaningful patterns like edges, textures, and shapes. And the diagram on the top side showed how convolution net layers progressively transform the input patches. So on the the bottom side of the images, it shows how the the convolution neural networks or the kernels detect the patterns of the images. So with the advent of the convolution neural network, the researchers have begun to apply it on the super resolution task. And CNN that is shown here that is proposed in 2015 was the first model to successfully apply CNN to image super resolution, and it is marked as a turning point in the field. The key idea behind SRCNN was to train a direct mapping from low resolution to high resolution images. The process worked in a very simple 3 stages. First, input the image was upsampled with bicubic interpolation and divided into overlapping patches. And the CNN learned to extract features presentations from these patches, as I showed you earlier, and applied a nonlinear mapping to transform them into high resolution features. This was quite groundbreaking at the time because it proved that the data-driven learning could outperform the interpolation. What I mean by classical methods. So even though SRCNN was relatively shallow, it has only 3 convolution layers, but it still produced much sharper results than bicubic interpolation. And then what happened next is the people tried to go deeper. That means more convolution layers. And to move on to other next step, I just wanted to highlight some of the meanings of this SRCNN. After SRCNN, researchers quickly realized that the deeper network could extract richer features and produce better superresolution results. And this led to VDSR, very deep super resolution, that is researched in 2016. So VDSR used a much deeper CNN, 20 layers compared to SRNSS, which was 3. This allowed the network to capture more complex features and structures in the images. Key innovation in that was that VDSR did not predict the entire high resolution image directly, that what has happened in the SRCNN. So instead, it just predicts the residue of the low resolution and high resolution. So as you can see on the image of the right, at the latest stage of the convolution layer, it shows the residue of the low resolution and the high resolution. And this residual learning approach made training faster and more stable because the network only need to learn the missing high frequency features like edges and textures instead of learning the whole entire images. So there was another great groundbreaking evolution. And that leads to the EDSR. The building on VDSR, the next step was EDSR, the enhanced deep learning deep super resolution. That was introduced in 2017. This model became one of the most influential CNN-based SR methods. So EDSR simplified the resonance-based structure by removing the batch normalizations layers, and EDSR also increased the number of feature channels, giving the network much stronger representation power. And this meant that capture finer details and more complex textures in images. And thanks to these kind of improvements, EDSR achieved the state-of-art results on major SR benches, including div2K and entire. And for several years, it was considered as the gold standard in the super resolution research. And there were some CNN-based super resolution methods were quite popular, but there was also another approach, which was based in GAN. So the next breakthrough came from GAN. So it's a generative adversarial networks. And GAN introduced a completely new way of generating realistic images that also transforms per resolution. And just to proceed with the GAN method, I will just give a brief time to introduce about the GAN and overall. So it's kind of two neural network. GAN is two neural networks competing in a two-player game. So the generator and the discriminator compete each other. So as you can see on the images, the generator acts like a counterfeiter. So it tries to create a fake money. And in our case, the high resolution can be considered as the fake money. And the discriminator is like the police. So it tries to detect counterfeits. And so in our case, it would be distinguishing between the real high resolution and generated high resolution images. So at first, both networks are very weak because they are not trained well enough. But as the training goes on, they push each other to improve. So the generator gets better at making realistic images, while the discriminator gets better at spotting the fakes. So eventually the generator becomes so good that the discriminator can easily tell the difference between the fake and real images. So SRGAN it's introduced in 2017. It was a milestone in the super resolution because it was the first model that uses the GAN method for this task. Earlier models like SRCNN and VDSR mainly focused on minimizing the pixel error using like metrics like MSE or PSNR. And this kind of methodology improved the sharpness, but it still produced some smooth images that do not look natural. But SRGAN changed the objective. Instead of just optimizing the PSNR, it uses adversarial training and perceptual loss to generate the images with highly realistic textures and look much closer to natural high-resolution images. And on the right side, you can see that the progression. So the left one is a bicubic result, and the middle one is the result from SR ResNet, and right one is the SRGAN. So it can so as you can see that the PSNR, the number on the middle is the PSR and SSIM, but you can see that even though the PSNR is lower in SRGAN, it can still produce much higher realistic result. So that also indicates that PSNR is not a very good metric for super resolution. But SRGAN is a very powerful tool, but it also has some limitation, strengths and weaknesses. So on the advantage side, SRGAN produces much sharper and more detailed textures compared to earlier methods. For example, like details like breasts and hair and building faces look much more realistic. But on the other hand, it also comes with some limitation because it tries to make images look realistic, so it can sometimes hallucinate details that were never present in the original image, and it makes some risky for scientific medical applications where the accuracy is critical. So, and another limitation for GAN is the training procedure. Training GAN is also known for its instability and computationally expensive. So it requires careful tuning and significant hardware resources. And now I go back to the CNN-based method. So after EDSR, the next big movement in CNN-based resolution came with RCAN, or Residual Channel Attention Network, introduced in 2018. So the main innovation here was the introduction of the attention mechanism in full resolution. RCAN recognized that not all feature channels are equally important for reconstructing high resolution details. So instead of treating every channel the same, RCAN uses channel attention module that you can see on the right side to learn which channels carry the most important information. And this makes the channel networks much more effective at recovering fine-grained details, especially in the complex images. So, and also RCAN is also built on a very deep residual network with using what's called residual in residual. So, which allows it to go very deep, extreme deep layers, like hundreds of layers, without training collapse. So it's also very strong to training obstacles. Sorry. And let's look at the strengths and weaknesses of the RCAN. On the advantage side, RCAN achieved state-of-the-art result in 2018 across several major SR benchmarks. And thanks to its residual in residual structure and channel attention modules, RCAN can go extreme deep. As I mentioned, the depth allows it to capture very fine details and complex features as well. But the power comes with a cost because RCAN is computationally very heavy. And since it relies on many layers and multiple attention modules, this makes it slower to train and more resource intensive. And also has slower inference compared to lightweight SR modules such as EDSR. And after CNN-based models like EDSR and RCAN, the next grand breakthrough in super resolution came from the transformers. CNNs process images locally using fixed size corners that can only see small neighborhoods nearby. And this was great for the textures, but it's some limited when we need to capture some of the global structures. And transformer changed this by allowing every pixel, or more precisely every patch of the images, to attend to every other pixels in the images. So this is done through self-attention mechanism. In practice, that means transformers can capture long-range dependency and global text context. And for instance, in satellite images, this helps preserving the structures like long rows, wind rivers, or coastlines that extend across the images. And so while the CNNs are excellent for the local details, the transformers bring in the missing pieces, global awareness. And this makes them extremely powerful for super resolution tasks that are both fine texture and also large scale constant matters. And here I introduced the HAT, or hybrid attention transformer. And it is one of the most recent state-of-the-art models in super resolution. It builds on an earlier vision transformer approaches like VIT or swing IR, but it introduced a hybrid attention mechanism. So the idea is to combine window-based local attention, which is computationally efficient, with global attention, which provides the context awareness across the whole image. So this hybrid design strikes the balance between accuracy and efficiency and make it practical even for very high resolution, super resolution tasks. In other words, the HAT brings together the best part of the both worlds. So the efficiency of localized attention and the power of the global context. So this makes it especially strong for recovering both fine texture and long-range structures in large images, such as faces or maybe urban layouts or satellite data. And today, the HAT sits at the top of the SR benchmarks, outperforming the CNN and other transformer-based methods. So this is the quite long summary of how the super resolution network has evolved over time, and especially with the advent of the deep learning technology. And from now on, let me introduce how our technology differs from previous methods. So what I have observed over time is that even though when we use the very state-of-art super resolution method, it's quite difficult. Sorry, it's quite difficult to reconstruct the very high resolution images. So this is one example. So the left image is the resolution, native resolution of 50 centimeter. And after we apply four times upscaling super resolution method, you can see that the details are not very much constructed. So, and the fact is more evident when you compare with the 25 centimeter GSD actual airborne images. So you can see that the details of the car is not very well recovered. So to overcome this kind of methods or this kind of problem, narrow space methodology is trying to use unpaired data set to train the super resolution network. So instead of using the paired matching low resolution, high resolution, we do not use so we use separate low resolution data set and high resolution data set. That means that the cell, so the high resolution image data set comes from, for instance, Pleiades, and the low resolution data set come from another satellite like maybe Planiscope or something else. And this kind of unpaired data set, the advantage is that since we use non-generic and realistic high resolution data set, it preserves all the details that it should have. So the super resolution network learns how to kind of make the realistic details in the while training. So that gives us some strong edges. And we have done some technology validation of our technology. So there was a Korea AI certification agency, and we have been certified that when you compare with the global state-of-art algorithms like HAT or EDSR that I had mentioned earlier, we have achieved much better sharpness, and we also achieve more number of detected objects after super resolution. And currently, we have various super resolution algorithm that is optimized for each satellite sensors. So we are producing from low resolution, including Sentinel-2 and Planiscope. We also have middle resolution ones and also very high resolution one as well. And here are some of the examples that I have. So this is the example of the Sentinel-2, which has 10 meters resolution originally. And after super resolution, it becomes like this. So this is before and after. You can see that the details of the oil tank is very much evident after super resolution. And this is the use case for the Planiscope that has 3 meters, and we can upscale it up to 1 meter. So this is before and after. And you can see that the contour of the container boxes are more clear after super resolution. And this is the use case for Pleiades Neo, which is the native resolution is 30 centimeter. And after super resolution, it becomes like this. So this is from 30 centimeter and to 10 centimeter. And you can see that the mechanical parts of the Eiffel Tower becomes much more crisper at super resolution. And I have brought some of the real world application for our super resolution. So the first use case would be object detection. We have observed that the after super resolution, the object detection accuracy increases from 20 to 30%. So as one example, you can see on here is this column shows the object detection result before super resolution, and this is the result after super resolution. And one of the tricky part or tricky task in the object detection is to differentiate these densely packed cars or densely located objects. But after super resolution, as you can see, it can successfully differentiate densely located cars without any problem. And this is another example for the ship. And similar thing can be done also in rent classification. And we have observed that 40% increase of the rent classification accuracy after super resolution. And this is the use case of using Sentinel-2. So the original image is Sentinel-2. And when we only use the Sentinel-2 native resolution, we have observed this kind of lens classification result. And as you can see here, this is actually the part of the urban area and with some of the apartments for the households. But as you can see here, the details are not very well expressed. But after super resolution, since it has better resolution, as you can see here, the text, the details are very well given. So super resolution clarifies roads and building edges while reducing error. And this is another great example. So as you can see in this part, this is the crop fields, probably rice. And in the original land classification, the details and contour edge of these crop fields were not expressed, but after super resolution, it is quite well expressed. Last use case that we have is the solar panel detection, or maybe a segmentation as well. And it can be also used to detect better and segment better solar panels around the area after using super resolution, as you can see over here. So there were some errors before super resolution, but after super resolution, the contours are quite well detected. And as the end part of my presentation, I'd like to have some potential introduce some of potential application that can be used for Indonesia. Sorry. So first sector would be agriculture. So agriculture is one of the most critical sectors for Indonesia, particularly rice self-sufficiency and palm oil exports. And one of the challenge of the traditional surveys is it's very slow and inconsistent, and especially difficult across the fragmented smallholder farmers. And yet the food price stability depends heavily on the accurate field forecasting and efficient subsidy allocation. So our solutions, when it's applied to Sentinel-2 images and plus some hyperspectral images, it can help to identify the crop fields accurately. And then after using hyperspectral images, we can also add some of the edge on the crop classification as well. From this, we can also deliver field level monitoring for yield prediction, pest or disease detection, and also acreage estimation. And the example on the left side shows the crop classification result that we have. And on the right side, we can also see that our yield prediction models have achieved the accuracy of around 95% when it is compared to USDA results in the US corn fairs. And this is another example that we can do is that on the left side, it shows the comparison between Sentinel-2 with hyperspectral vegetation indices on palm trees, and showing and also on the right side is the hyperspectral as more discriminative power, so that you can pinpoint where the palm oil tree has some problem or not. And on the right side is some of the hyperspectral data that can clearly separate different crop classes, supporting like precise classification and monitoring. And the next topic would be natural disaster management. So Indonesia faces frequent floods and landslides, volcanic eruptions, and cyclones as well. One of the main challenges is that is the cloud. So and cloud during the monsoon season makes it difficult for optical only monitoring unreliable. So but at the same time, the government and maybe insurance companies also need very rapid and accurate assessment to guide relief planning and financial recovery. So our service addresses this challenge by using multi-sensor approach. So first one, we use the optical super resolution that enhances the clarity of the disaster extents, such as floodwaters, wildfire scars, and damage prevents. And second, we use the SAR, or the synthetic aperture radar data that provides cloud penetrating imaging, which is especially important for mapping floods and detecting landslides during the very heavy rainfalls. And third, we can also implement the INSAR or interferometric SAR that can detect subtle ground deformation before landslide or volcanic eruption, enabling early warning system as well. So, and this is some of the use cases that we have for detecting the wildfire. This is use case for the flood that happened in North Korea. And this is the use case for the landslide that happened in South Korea. And this is the INSAR analysis data that detected the deformation after earthquake in Turkey. And we also, the next topic would be the marine resources, because marine resources are another critical sector for Indonesia, I believe. The country is one of world's top producer of the seaweed. But also sometimes disaster outbreaks and temperature structure continue to reduce the yields as well because of the global warming crisis. And also, I believe that illegal fishing is another huge issue, costing Indonesia billions of dollars each year while undermining the maritime security as well. And lastly, we also believe that mangrove and coral reef ecosystems are they are not the only biodiversity hotspots, but also they play a key role in blue carbon credits projects. And our service addresses these challenges in 3 ways. So first one, we combine the multispectral and high perspective data to monitor seaweed farms and agricultural ponds. And this helps them to track health and detect stress and improve productivity. And second, the images on the left side is the example of seaweed farm detection, and on the right side is a correlation analysis between sea surface temperature and seaweed production in South Korea. So South Korea also produces much of the seaweed in the southern part of South Korea, but the sea surface temperature is becoming a quite big issue and decreasing the productivity of the seaweed. And the next slide, there are also 2 images that shows the on the right side, you can see the example of the vessel detection using SAR images, which works even at the night and also under cloud cover. And also we also produce high resolution maps of mangroves or the coral reefs, as you can see on the left side. This is the use case of the Cô Chien River in Vietnam, and where it used to be the very large area for mangrove, but now it is turned to the shrimp farms. So the red part means that the mangrove area was being destroyed by these shrimp farms. So this kind of mapping can be also done using the satellite images. And lastly, Indonesia is also one of the global leader in mineral resources, especially nickel, I believe, and which is a critical material for electric vehicles, batteries. And this sector also faces some major challenges as well because of the illegal mining and deforestation as well. And also, so our service can also help to address these issues using the satellite image solutions. And for instance, what we can do is that we can apply full resolution and object detection to monitor nickel mine expansion, also detect illegal mining activities as well, as you can see on the right side. So instead of doing the on-site visit, which costs time and or cost as well, we can just use satellite images to monitor what kind of the mining activity is being done on the site. And another image that is showing on the bottom is a very interesting use case. So it was a use case coming from from actually Africa. So the color part shows the heat map of the traffic nearby the mining area. And one of the core problem of that area was the congestion of these trucks that deliver the minerals. So the mining activity is fine, but whenever there was a congestion of the traffic and of the trucks that deliver the minerals, it causes some of the risk in the transporting this kind of minerals to other countries, and it causes some risk for the investors. So we have used very high resolution images to detect the trucks that causes congestion, and then deliver this data to the producers and investors, and they can know ahead what is happening there and what causes such congestion, and then lower the risk of the mining activity. So this is end of my presentation. Thank you for listening, and thank you for your attention. And I hope that we can have some better discussion later to know much better of each other's technology. Thank you.
Okay, thank you, Mr. Kim. Okay, for that comprehensive presentation on the technology foundations and industry application of superresolution in satellite imagery. Your insight into the practical challenge and commercial viability of superresolution techniques provide an excellent foundation for our discussion. Okay, participants, ladies and gentlemen, here some summarized takeaways from the Mr. Kim presentation. Mr. Kim began by explaining how classical methods such as interpolation techniques were the earliest attempts to enhance image quality. While these methods were simple and fast, they often produced blurry and blocked results. Over time, the field shifted toward deep learning approach, including CNN, GAN, and more recently, like transformer-based model. Each step in this evolution has allowed for greater accuracy and finer detail recovery, though often at the cost of higher computational requirements. Mr. Kim also highlighted the limitation of the current methods, while deep learning-based approaches have shown state-of-the-art results. They still face challenges such as the higher training costs, limited clearance across different satellite sensors, and in some cases, the risk of generating artificial features that may not exist in the original data, like in the GAN model. From an industrial perspective, however, the opportunities are significant. Super resolution can unlock much greater value from existing satellite assets without the need to launch entirely new spacecraft. This means lower cost and faster development of higher quality imagery, which is essential for industry like agriculture, mining, disaster management, and national security. Mr. Kim provide example for real application, such as improving object detection, essential classification, and detecting infrastructure like solar panels more effectively. He emphasized that these improvements aren't just academic exercise. They have tangible benefits in decision-making, environment monitoring, and economic development. In short, Mr. Kim talk demonstrated that while super resolution has clear computational challenge, its strategic importance in Earth observation industry is undeniable. Is it a field that's continue to evolve rapidly, and we can expect to see a greater adoption and innovation in the year ahead. Now, let me introduce our second speaker who will complement this industry perspective with academic research insights. Professor Danang Surya Chandra, SSI, MSc, is a research professor and head of the research group for geodata at the Research Center for Geoinformatics, BRIN. Professor Danang earned his bachelor degree in mathematics from Universitas 11 Maret in 2002 and his master's in remote sensing and GIS from Beihang University, China in 2010 and completed his PhD in remote sensing from the University of Queensland, Australia in 2019. Beyond his research role, Professor Danang served as Indonesian national contact point for the group on Earth observation, or we call GEO, and GEOS, throughout in NASA Secretariat BRIN. His research portfolio encompasses remote sensing, GIS, artificial intelligence, machine learning, and deep learning applications. He has led numerous international and national projects, including the Crop Biodiversity Project with UNESCO, Marine Waste Mitigation Studies with Australia Connexi Program, and SAR data processing methodologies for agriculture monitoring. His scientific contributions include 11 registered and granted patents and 11 software copyrights for satellite image processing, and also presents an international conference across Japan, Malaysia, China, USA, and Europe. This extensive research background makes him ideally positioned to discuss the scientific foundation and validation process for super resolution in remote sensing. Good morning, Professor Danang.
Good morning, Mas Yohanes.
Okay, Professor Danang, please share your research findings and perspective on super resolutions application in remote sensing. The floor is yours for the next 45 minutes. Thank you.
Thank you, Mas Yohanes. You can see my screen?
Not yet.
Oh, what?
Okay.
No, okay. Thank you. Good morning, everyone. My name is Danang Surya Chandra. I'm a researcher at Research Center for Geoinformatics, National Research and Innovation Agency of Indonesia, BRIN. Here, I'm going to present about enhancing spatial resolution of satellite imagery by using image fusion and super resolution, and I will compare between them. The first big question is, why do we need to enhance spatial resolution of satellite imagery? Is it necessary? Is it important or not? The answer is yes, because by enhancing spatial resolution of satellite imagery, we can improve visual interpretation. Higher spatial resolution makes features on the satellite imagery more distinguishable, such as roads, buildings, and agriculture plots. It also enhances visual analysis, especially for urban planning and disaster and environmental monitoring. By enhancing spatial resolution of satellite imagery, also makes classification and mapping more accurate. Higher spatial resolution can improve land cover and land use classification, and it also allows detection of small-scale features like narrow rivers, individual trees, or small structure that low-resolution images cannot capture. And it also supports in precision agriculture, environmental monitoring, and disaster management as well. And it is compensating for sensor trade-off. As we know, many satellites sacrifice spatial resolution in an exchange for spectral richness or frequent acquisition. So spatial resolution enhancement methods such as super resolution may help to overcome these limitations without the need for new satellites. If the enhancing spatial resolution of satellite imagery important, so the second big question is how to enhance spatial resolution of satellite imagery. We have two ways. First is by using image fusion, and the second is by using super resolution. Image fusion combines multi-images, commonly from high resolution and low resolution images, into a single output. This output preserves spectral quality and enhances spatial detail, and it is making the imagery more informative and useful for many applications. On the other hand, super resolution improves the spatial quality of satellite imagery by reconstructing fine details from a low resolution image. making the information more valuable and applicable across many fields. First, I'm going to explain about enhancing spatial resolution of satellite imagery using image fusion. I'm going to explain briefly about image fusion. Image fusion is a technique used to integrate information from multiple satellites, commonly from panchromatic and multispectral images, to produce a single higher quality image. There are some benefits if we use this method. This method produces a higher spatial detail and preserving spectral quality. And it also improves visual interpretation, and it also increases performance of automated classification analysis. But there are some challenges, and the output may has spectral distortion, especially if not handled carefully. And it has computational complexity as well for advanced methods, and it depends on accurate image characterization. I'm going to explain briefly several image fusion, the common several image fusion. First is intensity hue saturation fusion, or ISS. First, we have to convert the MS, the multispectral image, from RGB to ISS space, and then replacing the intensity component with the high resolution panchromatic image. And the last is convert back to RGB. So in the last step, we will have fused image. And the second is PCA, principal component analysis fusion. First step is performing PCA on the multispectral bands, and then replacing the first PCA with the panchromatic image, and after that applying inverse PCA transform to get the fused image. And third example is wavelet transform fusion. By decomposing panchromatic and multispectral images using wavelet transform, after that replacing high frequency detail components of MS with panchromatic images, and the last step is reconstructing fused image with inverse wave transforms, and then we will get the fused image. And the fourth method is proof transform fusion. This is the simple one. By normalize MS band and multiplying them by panchromatic image, it helps preserve spectral characteristic and improving spatial detail. We develop a new method for image fusion called Fusion Plus. Fusion Plus is multi-sensor image fusion for very high resolution satellite images. We use spot 6 and playouts for the experiment. And this is the flowchart. First, we do upscaling from low resolution image, and we do weighted dimensionality reduction to get synthetic HR. And then we do shift assessment between higher resolution image and synthetic HR, and we will get adjusted HR, adjusted synthetic HR, and adjusted upscale LR. After that, we do convolutional using kernel of image enhancement, and we will get the enhanced HR. After that, we combine between this result and adjusted synthetic SR. We also do sharpening of adjusted upscale LR, and we do histogram specification of both of the results. And the last step, we will get the fused image. we conducted some experiments of this method. The study area are in Jakarta and Bandung. These are the results from each stage of fusion plus. This is the results of image fusion from spot 6 multispectral and panchromatic. And we have compared between other methods such as wavelet, Ehler, modified ISS, HCS, and SPF. We can see clearer if we zoom in some object. For example, in this building, we can see that fusion plus has clearer and detailed image compared to other methods. And we also conducted another experiment, image fusion from spot 6 multispectral and players panchromatic. This is the result, and we also compare to other methods. We can see clearer that this is spot 6, the original of spot 6 multispectral image, and this is the results. If we zoom in some building, we can see that the result has more detailed, clearer image. If we analyze the raster histogram of the original and fused image using Fusion Plus, we can see that the raster histogram from original image and the result of the Fusion image, Fusion Plus, have a similar histogram. And then for a statistical assessment of fused image using Fusion Plus, we can see that the mean and standard deviation, the blue and red one is the mean of spot 6 multispectral and the mean of fused image by Fusion Plus. For pen 1, 2, 3, and 4 look similar. And for standard deviation, we can see that the standard deviation of the original image of spot 6 multispectral and fused image by Fusion Plus are also similar on each pen. So we can conclude that Fusion Plus method increases the spatial detail of the original image and preserving its radiometric consistency. And as a result, the fused images from Fusion Plus have a maximum detail increase, minimum color distortion, and a natural color appearance. And in the second part, I'm going to explain about enhancing spatial resolution of satellite imagery using super resolution. The big question is super resolution really useful, especially for real life? The answer is yes, because super resolution has been widely used for many applications, most commonly used in medical imaging, surveillance, media industry, and satellite image processing. You can see in this image, super resolution is used for MRI in medical imaging. You can see in the original low resolution, it's not clear, it's still blur, but by using super resolution, we can increase the detail of the image. This is the result of the DL generated super resolution. And this is another example. In surveillance application, we can see that the number of on the vehicle license plate is blurred in this photo, but using super resolution, we can see clear and detail the number on the license plate in here. The two big company, Maxar and Airbus, also use super resolution. Maxar has HD technology, and this technology delivers clearer images for faster, more accurate data extraction, enabling advanced analytics and machine learning, and confident decision making at a global scale. This is one of the example. We can see this is the before the image in using super resolution, and this one is the result of super resolution. We can see that the result of HD technology in the super resolution application is more detailed and clearer. And this is another example in urban landscape. This is before and this is after. Airbus also use super resolution technology called HD15. This is the results of HD15. HD15 performs image restoration rather than artificial enhancement, ensuring reliable artifact-free result. This is Players Neo. And I'm going to explain briefly about super resolution. Super resolution enhances spatial resolution by reconstructing high resolution images from low resolution data. The important is this technique doesn't need requiring new sensor, so we can apply this method only using only one image, and by recovering fine-grained features, super resolution improves image clarity and accuracy. And then by using deep learning, offer significant improvement in resolution quality. But there are some challenges that if we use super resolution using, for example, deep learning, it has high computational costs, and the results may risk of generating artificial details. There are we can categorize into two main groups of super resolution methods based on how they construct high resolution images from low resolution inputs. First is interpolation-based method, and the second is learning-based method. In interpolation-based method, there are some techniques. First is nearest neighbor, and then bilinear interpolation, and the best one is peak-to-peak interpolation. The advantage if we use this method is it is simple, fast, no training required. So we don't need to create a training sample or training data set. But there are some drawbacks because it cannot restore fine texture or details, and the result often still blurry. On the other hand, learning-based method usually use machine learning, especially deep learning, to learn a mapping from low resolution to high resolution images. There are some methods such as CNN, GANs, and transformer as well. The advantages are that this method produce the best quality of image, state-of-the-art performance, and can adaptable to domains, especially for remote sensing and medical. But there are some drawbacks. This method require a large training data set, so it has high computational costs, and it may produce artificial details as well. In the super resolution research, we have conducted the experiment using learning spatial spectral prior network of spatial resolution, or we can call SSPSR. This method uses a deep neural network based on a spatial spectral prior network to fully exploit the spatial information and correlation among the different spectral feature. So in this first step, for the input processing, the low resolution image is divided into overlapping groups in this one. So this one. In our experiment, we divided the image into 27 pages. And then in branch networks, each group is processed by a branch network to extract spatial spectral feature and perform initial upsampling this network. And then in feature fusion, outputs from all branches are concatenated and fit into a global spatial spectral feature extraction and upsampling network. So the output of each network will be concatenated, and then in rich contraction layer inserted after each branch upsampling model to maintain a consistent structure between the branch and global network. This one. And in the residual design, this residual design uses short, long, and global skip connection for flexible information flow. This one. And the last, for parameter sharing, branch networks share parameter across groups, reducing computational cost and simplifying training. So this method has effectiveness because ablation studies verify the contribution of each component and the fusion strategy. And this one is the network architecture of the each spatial spectral block or SSP. This one. This SSP use deep neural network, and for the channel attention module use this method use transformer. This is the result. We have some resultant images. This is low resolution, the original image, and this is the result of the SSPSR. We can see that the results has more detail and clearer, and we can identify easier each object in this image. If we compare to the truth image, we can see that both of them have high similarity. We can see in the another results, this one, in the urban area. This is low resolution image, and this is the result of super resolution, and this is the ground truth. You can see that the housing is more detailed, and we can identify easier in this result. And we can see that if we compare between super resolution image result and ground truth image, we can see that both of them have a high similarity. And this is another result. We can see that this is the in agriculture area. We can see that the boundary of the rice field is still blurry in the low resolution image, but we can see in the super resolution image, we can see that the boundary is more firm and detailed. And if we compare to the ground truth, they have high similarity. This is another results. This is also another result. We can see that the building of the low resolution image is still blur, but we can see in the super resolution result, the building is more firm and more detailed. And if we compare between super resolution image and ground truth image, we can see that they have high similarity. And this is the result of the statistic assessments. So we can conclude that deep neural network based on a spatial spectral prior network is used to address the single image super resolution problem, and to address the issue that the training samples of image are limited. For example, in our experiment, only use 27 pages. A group convolution with shared network parameters and progressive upsampling network is proposed. An experiment conducted on several datasets demonstrate that the model attains performance with respect while simultaneously producing a high-resolution reconstruction that exhibit superior perceptual similarity to the ground truth. This is the last. I'm going to compare image fusion and super resolution. I think the goal is quite similar, and the strength of between them in the image fusion. Image fusion can balance spectral and spatial quality, widely used and proven methods. On the other hand, super resolution works with only low resolution input, only a single image. We need only a single image, and it's significant improvement with deep learning. And they have a limitation in image fusion. The limitation is that requires multiple input images, such as panchromatic and multispectral, and then it has risk of spectral distortion. On the other hand, in super resolution has high computational costs and may risk of generating artificial feature. That's all from me. Thank you.
Okay, thank you, Professor Danang, for the insightful presentation on the research dimension of super resolution in remote sensing. Your analysis of evaluation metrics, dataset consideration, and application-specific optimization provides crucial scientific grounding for implementing these techniques. Okay, here are some summarized takeaways from the Professor Danang presentation. Professor Danang compared two major approaches. First, image fusion, where the high-resolution panchromatic images are combined with lower resolution multispectral image. This method preserves spectral quality while enhancing detail, but must be carefully implemented to avoid spectral distortion. In the second, super resolution, which reconstruct fine details directly from low-resolution data, often using deep learning models. And super resolution is powerful because it doesn't require multiple sensors input, but it does carry risks such as generating artificial features and requiring high computational results. A key theme in his presentation was the importance of scientific reliability. In applying these methods, researchers must carefully validate results and ensuring that enhanced detail are trusted and not misleading artifacts. He emphasized that these considerations are especially critical when data is used for policy planning and disaster response. Professor Danang then brought the discussion closer to home by presenting application in the Indonesian context. Throughout case studies in Jakarta and Bandung, he showed how Fusion Plus and super resolution methods improve land classification, urban mapping, and environmental monitoring. He also highlighted specific application areas vital in Indonesia like precision agriculture, disaster management, monitoring and infrastructure, and urban planning. His presentation reminds us that technical innovation must be paired with local relevance. The Indonesian examples has shown how these methods can directly benefit communities by improving food security, disaster resilience, and sustainable development. In summary, Professor Danang's presentation was a blend combination of scientific rigor and practical application. He challenged us to think critically about how we ensure reliability while also showing the transformative potential of super resolution in Indonesia's unique geographic and social landscape. Now, we move to our interactive discussion session. This is your opportunity to engage directly with our expert on super resolution technologies. Here are some guidelines for discussion today. For Zoom participants, please use the Q&A button or raise hand and unmute when invited to speak. And the second, for YouTube viewers, submit questions through the live chat. And for the question scope must be focused on the technical, methodological, or application aspect of super resolution. And please keep questions concise to accommodate multiple participants. And please feel free to ask in English or Bahasa. Okay, maybe let me start with some first questions, key questions that write both presentations. Mr. Afias, can you share some questions from the Q&A? Okay. I think there is 3 questions. First from the Andi Ibrahim to Mr. Kim. The question is to what extent can we ensure that the process preserves the original reflectance values of the satellite imagery rather than just improving visual sharpness? Maybe you can answer this
Yes.
question.
Yeah. Thank you for the question. So I think it may depend on the radiometric resolution of the image that we use, but from my past experience, when we apply the resolution on Sentinel-2, it showed very low SAM result. That means spectral SAM means spectral angle mapper, and if the difference degree between two images is lower, the spectral matches more. And based on my experience, the SAM was really relatively very low when we compared when we applied super resolution only. So, but as I mentioned before, it really depends on how you train your super resolution network. So, for instance, if you use the GAN-based method, it may create very different histogram of the result based on super resolution. So, to just summarize, it's best to select a super resolution network that matches that minimize the color difference or histogram difference, and then try to use the very some kind of loss metrics that can reduce this difference after super resolution.
Okay, thank you, Mr. Kim. There's another question from the Elino Gardandiarnoro to Mr. Kim.
Yeah.
First question is from little bit technical from using CNN attention. Could you explain more detail that how to do multiplication on the convolution? Is it multiplication by the features or the weights or filters? And the second, for the transformer and pixel base, you mentioned such embedding, which means that a pixel should be enriched in subspector. How do you do that? Or do we just select embedding from the window? Give your opinion. And the third, when we do a super resolution, the new data may have a different gradient of sun illumination or brightness. What do you think on that case when we use the transformers for super resolution?
So just to begin with the first question, just to let you know that in a very standard convolution, you slide a filter over the input feature map. So at each position, you just compute a dot product between the corner weights and the local patch of the feature map. So it's just a simple multiplication. So it would not be difficult to find how to do the multiplication. And for better, more concrete explanation, I advise you to look into some of the GitHub repositories to find how the attention CNN that use attention module and see how they implemented this kind of product. And then the second question is, so regarding the embedding, so the transformer modules, transformer network, they produce vector embeddings in such ways. So first of all, they just divide the images into patches. So for instance, like 4 by 4 pixels or 16 by 16 pixels, and they flatten it each patch into a 1D vector, and then they apply just linear projection or maybe matrix multiplication to map this vector into an embedding space. And then lastly, they add the positional encoding so that they can the model knows where the each patch is. So in summary, they just this transformer embeddings, they're produced with following procedures within the network. Yeah. And the last question is, when we do super resolution, the new data may have different gradient of sun illumination brightness. And I think that even though the new data, when we do the inference on the new data, and even though it has some different lighting conditions, I think it's okay to implement the transformers based super resolution, because I believe that the transformers super resolution is quite robust to this kind of different image conditions. And also and before that, I think it's best to train this kind of like edge cases as well while training this super resolution network, because as you know, the more data and more additional data and more edge cases that the super resolution network learns, it becomes more robust, and that means it can handle more edge cases, and when it is actually being inferred and in the production level. Yeah.
Okay, thank you, Mr. Kim. The third question from the Ahmad Marianto to Mr. Kim also. If we aim to generate a 20 centimeters resolution image from an image with 20-meter resolution, what the minimum number of the image scenes require?
Yes. Also, thank you for the question. Before answering this question, I advise you not to implement from 20 meter to 20 centimeter, because of what there's a too much gap, information gap between these two images. So there is a high chance of the making like artifacts or hallucination that is not contained in the low resolution images. So based on my past experience, the optimal ratio between low resolution and high resolution is between two times or to 4 times. So if it goes beyond that, the probability of creating uncontained information goes higher. And just to answer to your following question, the number of scenes that is necessary for the training of the super resolution really depends on the super resolution network that you're using. So in our case of algorithm, we only need like 3 to 5 full scenes of the images to train the super resolution network. So it's quite low. But in case of other super resolution network like EDSR or HAT, I believe that, or even transformer-based as super resolution, I believe that the number of data sets should be go higher over like, I'm not sure, but over thousands or 10,000 levels of the images that you may need to train the super resolution network. Yeah.
Okay, thank you to Mr. Kim. Okay, I see another question from the Lino Garda in the Q&A button. About a gun, the generator source is from the random noise. How to maintain the input image as low resolution to produce its super resolution?
Um, So I think it depends on how you make the structure of the GAN, and I think in my case the input image, so the input data was not the random noise. So in general, I know that in general GAN based networks, they usually start from the random noises, but in the case of task of the super resolution, the input is normally the raw resolution images. So I think, yeah, that solves your question.
Okay, thank you, Mr. Kim. Are there any questions from the participant? I think not yet. Okay, maybe let me ask some questions. Okay, from to both speakers. Given the different super resolution approach discussed today, from industry implementation to research validation, what do you see as the most critical factors for ensuring that super resolution products meet scientific standards for quantitative remote sensing application? Maybe from to Mr. Danang first, you can ask this question. Answer this question.
Thank you, Mas Johannes. Yes,
Okay.
we had to assess the results of the super resolution that we conducted by using, for example, SSIM for the similarity, and we can see that if the result has a high SSIM or similarity between the original image or the grounded image and the fused image, not fused image, super resolution image. So the result will be good and can be used to the next application. So the important factor, if we have to do the analysis or assessment of the super resolution results. That's all from me, Mas Johannes.
Okay, thank you, Mr. Danang. How about you, Mr. Kim?
So in my case, I think in order to ensure the usability of the super resolution result is that I think I have mentioned that PSNR and SSIM as some of the metrics for the result of the super resolution. But as I mentioned earlier, and as we can see from result of the SRGAN, the PSNR and SSIM is not the absolute metrics to kind of to identify the quality of the super resolution, because sometimes the lower PSNR images show better or more realistic details of the images. So in that sense, and based on my experience, I advise researchers and others to actively use the visual inspections on the super resolution visual because I think our human inspection and human visual inspection is the best way to ensure the result of the super resolution, and we can instinctively know whether this result is radiometrically coherent with the original images and whether it produces unnecessary artifacts or not. So I try to use the hybrid of the SSIM and PSNR, but also rely heavily on the visual inspection.
Okay, thank you, Mr. Kim. Are there any questions from the participant? Please feel free to ask in English or Bahasa. You can use the Q&A button or raise hand. Okay. Maybe I would like ask another questions. To both speakers. What specific validation strategies would you recommend when implementing super resolution techniques for different domains like agriculture, forestry, disaster monitoring, or urban planning? Maybe you, Mr. Kim first, you can answer this question.
So as I mentioned on my presentation, I believe that super resolution is a very unique technology, but it can be better implemented when it is used with another use cases like object detection, classification, and segmentation. Because when I meet my customers, what they usually say is that so what's next of the super resolution? So they are not. So the end goal of their super resolution is to actually have better analysis results. So that's how I also try to make many use cases of the super resolution. And in that sense, I think before implementing this super resolution to maybe agriculture, forestry, and other things, I believe that the most important thing is to have a very robust and high-performing super resolution network. So, but because otherwise, if the super resolution network is not robust and it creates unnecessary details and artifacts, it may affect the next step. So it may even cause errors in the object detection, classification, and such on. So before moving on to other sectors and implementing other use cases, I'd advise you to have very good, robust super resolution network. And I think in order to make a robust super resolution network, it's best to have many hours invested in picking up the training data set, because I believe that the result of the super resolution is very much critically linked to the quality of the input data. Thank you.
Thank you, Mr. Kim. Maybe Mr. Danang, you can answer these questions. Professor Danang.
Yeah, to prove the robustness of super resolution method, we must have variety of object on our image, such as building, vegetation, and then crop and others. So we can prove the robustness of the method. We have to we can evaluate with each object to prove the reliability of the method. We also must do the two assessment. First is visual assessment. I agree with Mr. Kim that visual assessment is very important in this case. And then we also must do the statistical assessment, so we can see in the the mean and then the deviation standard deviation, and also like the SSIM and the similarity of both of the images, the image from the result and the image from the ground truth. If the result and the assessment show the high accuracy, I think the method can be used for the application for variety application in the next needs.
Okay, thank you, Professor Danang, for the answer. Okay, are there any questions from the participants? Let me see the chat or the Q&A. Okay. If there is no other questions from the participants, maybe we can move to closing statement or closing discussion to the webinar in today. Okay, before we conclude, I would like ask each speaker for their final thoughts. So, Mr. Kim, what emerging trends in the commercial space sector do you anticipate will further advance super resolution capabilities?
So it has been since we have been developing this resolution technology since 2019. So it has been like almost 6 years, but personally, I sense that the demand of the resolution technology is growing a bit more after years, and I believe that this resolution technology is can be a very powerful tool to help the countries that may not have their own satellite, but the countries may need the satellite data for their, for instance, urban planning or like agriculture usages. And I believe that when we combine the resolution technology with the like public data like Sentinel-2, Landsat, or even MODIS, I think this can be a very cost-effective and a very good alternative to use the commercial data set. And that can be one trend that I sense. And on the other hand, since the commercial satellites there, the satellites spatial resolution is getting better and better overall. So I believe that there may be, but even though the spatial resolution is growing higher, I believe that in some cases like defense sector, they may need more high resolution overall. So I think in that sense, even though the spatial resolution sensors spatial resolution goes higher, I think the demand of the higher resolution images will sustain. So I believe that in the case of spatial resolution can be one good technology and very useful technology. Yeah, thank you.
Thank you, Mr. Kim. Okay, I see some questions from in the Q&A questions. It's from the Lino Garden Denaro. Dr. Lino, for Prof. Danang, I saw from the figure that from LR image input and then separated by 3 branches, each of them are overlapping, which means each branch has different information. Is it true? Then what the implication of doing this way? Additionally, I saw from figure about F group, is it kind of from the input LR image? Please, Mr. Danang, you can answer these questions.
Thank you, Mas Lino. Yes, for the 3 benches, they have different results, and that's why after the process, we merge the results. The results have different information, especially for the spatial resolution and the spectral resolution as well. And the implication that the model will have the rich information of the spatial and radiometric information of the input image.
Okay, thank you, Mr. Danang. Okay, the next questions from Mr. Dede, Dr. Dede Dirgahayu to Minsik Kim. How many maximum size of square area to process data Sentinel-2, 10 meters to super resolution 1 meters?
Yeah. So for our case, we have only tried to upscale the center to images from 10 meter to 3.2 meter. So it is around 3 times upscaling. And so the maximum area of processing really depends on your hardware capability. So if you have big GPUs, then that means you have better, faster, and more capability to generate the processing. And in our case, we have tried to produce the base map of the super resolution Sentinel-2 images of the whole Korea. And it took almost 4 hours to produce whole Korea, including North Korea and South Korea. So I think that may give you some idea on how maximum size of the area that we can process. Thank you.
Okay, thank you, Mr. Kim. Are there any questions from the participants? Before we continue to the final thoughts from Mr. Danang. Okay, I think I don't see any questions. Let me see first. Okay. Okay, I think I don't see any questions in the Q&A box and the chat box. Okay, there is no question too on the YouTube. Okay, maybe I will ask for the final thoughts to Professor Danang. From a research perspective, what are the most promising directions for the advancing super resolution methodologies specific to tropical and archipelagic environments like Indonesia?
Yes. As we see that the two big company, Maxar and Airbus, use super resolution. So I think super resolution is already proven. So we can apply this method to our areas in Indonesia, because Indonesia has a very big area. So, and we monitor Indonesia area usually use medium resolution such as Landsat 8, 7, 8, 9, and then Sentinel-2. So if we so we can improve the scale of the information using medium resolution. We can use super resolution to increase the spatial resolution of the medium resolution to high resolution. So the information can be more detailed, and we can interpret the objects more accurate. And we can do like classification, automatic classification, more accurate as well. So we can do monitoring for Indonesia area more accurate.
Okay, thank you, Mr. Danang. I think I see the question in the Q&A box. I think this is the last questions, right? For because it's already 11 o'clock in Indonesia. There's two questions to both speaker. First, how could we design evaluation criteria that account for topological ecological integrity, such as road connectivity or watershed continuity? And the second, can you share your opinion on should we focus more on making models topology over during training or on developing post-processing corrections that restore valid topology? Maybe we can first answer maybe from the Mr. Kim.
Can I ask to the questioner to elaborate on the logical integrity? I'm not sure how I understood it correctly.
Okay, Komite, can you add the Mr. Zizal to this session?
Does it mean that the kind of like geographic awareness or something like that? Or
Hi, can you hear my voice?
Yeah.
yes.
We can
Okay,
hear.
sure. I just want to clarify on the topological integrity because my study was based on morphology. So what I mean on the topological integrity, for example, when we generate a higher resolution imagery, sometimes there are fragments in road or railways, and sometimes when we working on two different subset of two different scenes on imagery, sometimes there are merging errors. So I just want to ask your opinion, should we address it on the training phase, or maybe later we do a post correction after that, which I just want to ask you, because yeah, it is important for me when we're trying to study it on the morphology section. Thank you.
So I guess this question is related to the kind of consistency of the scenes when applying spatial resolution, and I believe that this kind of care should be done on the both sides. So first one, as you mentioned, the picking up the right conditions. Right, the data set is most important. Based on my experience, and second, there are some methods to kind of hint how do I say to prevent such kind of inconsistency when applying spatial. For instance, what I normally do is that I overlap the scenes, kind of like, for instance, like 15 pixels by 15 pixels when I do the super resolution processing. It may take a bit longer time to process because there are some overlapping patches, but this kind of overlapping helps us to kind of produce very consistent and consistent and non-artifact images as a spatial resolution result. Yeah.
Okay. Thank you for the answer, Mr. Kim. And how about you, Mr. Danang?
Thank you, Mas Yusel. So, in my opinion, in the beginning, we must do the image correction. So, the machine, like deep learning or machine learning, will learn correct information between lower resolution and the target image, and then we can apply our spatial resolution method. So the result will not have any issue of the topological integrity.
Okay, thank you, Mr. Professor Danang. I think there is no questions again for the Q&A and chat. Okay, thank you to both our speakers, Mr. Min Sik Kim and Professor Danang Surachandra, for the sharing their valuable expertise on super resolution in remote sensing. Your presentation have provided our community with both practical industry insights and rigorous scientific perspective on this transformative technology. To our participants, both via Zoom and YouTube, thank you for your engaging questions and active participation in advancing our understanding of super resolution application in geoinformatics. The discussion today has highlighted the significant potential of super resolution techniques to enhance our analytic capabilities using existing satellite data source, particularly relevant for Indonesian diverse geospatial challenge. Now, I return the session to our MC, Mr. Dedi, for the closing remarks. Thank you.
Okay, thank you. Thank you, Mr. Kim. Thank you, Mr. Danang. And thank you, Mr. Yohanes, for hosting the BRIN event today. Okay, practitioner. So that was the series of event for BRIN today. We hope that what has been conveyed by the head of the Geoinformatics Research Center and the speaker today, and everything we discuss will be beneficial and increase our collective knowledge, especially about enhancing satellite imagery, the power of super resolution in remote sensing. Okay, ladies and gentlemen, let me close this event with a pantun again. Indah memang bunga selasih, harum semerbak di pagi hari. Cukup sekian dan terima kasih. Semoga kita bisa bertemu kembali. Bila menanam pohon kenari, gelap tenggelam menjelang subuh. Izinkan saya pamit undur diri. Wassalamualaikum warahmatullahi wabarakatuh. We look forward to seeing you at the next webinar with other interesting topics. Thank you to practitioner for your presence. See you next time and bye-bye.
Thank you, Pak Dedi.
Thank you.
Thank
Mas
you, thank you, Mr.
Yohanes.
Yohanes.
Thank you.
Mr.
Thank you,
Kim,
thank you,
Kim,
Mr. Kim.
and all
Mr.
participants. Thank
Danang,
you.
Yes,
Thank
thank you,
you.
Mr. Danang. Thank you. Thank you, Mas Alkes.
Ya, Pak. Thank you.
Izin lip ya.
Ya, terima kasih, Pak.
Sama-sama.